Hi, I'm Lawley, representing the Teachable AI Lab at Georgia Tech, and I'm about to present VAL, the Verbal Apprentice Learner. VAL is a technology we developed to support humans teaching computers how to perform tasks using natural conversation. We also designed it so that the learned task knowledge is interpretable, generalizable, and modifiable. Ideally, anyone should be able to teach computers how to do tasks, not just people who can program or train massive ML models. VAL can be wired to primitive actions in an environment, like key presses in video games or mouse movements on a computer, and VAL can then learn complex tasks that use those primitive actions. VAL learns the tasks via natural language instruction, where the human explains the task, and VAL asks clarifying questions until it understands. Some specific values are then converted to variables so that VAL can perform the task in different scenarios. These variables are one piece of VAL's hierarchical knowledge structure, which is designed to mirror the structure of the learning conversation so that people can interpret it easily and make edits to the knowledge if necessary. While natural language is not the only way to learn tasks, it's the way we focused on here so that we could make use of the frankly meteoric rise of large language models over the past few years. VAL was inspired by the ITL framework, Interactive Task Learning, in which natural interactions with humans transfer knowledge to computer-based learning agents. ITL is a general framework that supports many communicative modalities, including gestures and visual diagrams. With VAL, we focused on the language modality because of, again, the rapid progress of language understanding techniques in the last couple of years. So, past ITL systems used a classical approach to language understanding that probably a lot of people are familiar with. So, basically a progression from syntactic to semantic analysis using a chain of discrete components, which can be kind of error-prone and brittle. Lots of things can fail to parse in these kinds of NLP pipelines, and so there's always been a strong focus on more fluid language understanding techniques. So LLMs also can be error-prone for reasoning, but for the analysis of the meaning of language at a sort of syntactic semantic level, they are quite powerful, and we would like to use them as a tool to sort of boost the ITL approach by replacing the classical NLP pipeline, but keeping the reasoning structured and symbolic without delegating that to the LLMs, because it's shown that they can't do reasoning in every scenario. So language has some other benefits. For one, conversations have a hierarchical structure. There are subtopics, and you can branch off and return to the original conversation. And they also have a natural binding of words to actions, which, as you explain a new action, you naturally are giving it a word, which VAL can use to label it and create an understanding of what that word means. This is sort of allows for an interpretable knowledge structure where the word is assigned to the action when you view the tree. The symbolic knowledge structures that VAL learns can also be generalized, even only with one example. So using some heuristics and some LLM judgments about which parameters can be generalized, you can figure out which things should be variables and which things should be constant, even given one specific instance of a task, which is more than can be done usually with a single example in a massive ML system. So also the flexibility of LLMs when it comes to parsing and understanding informal language, we think enables a wider variety of users who might not all speak in the same way, to use the system. They don't need to conform to the formal grammar of English. The LLM can be resistant to some things and even extend to other languages or mixes of languages. So before we dive into how VAL works on a technical level, I'm going to show you this video so you can visualize the system. Here I'm explaining to VAL how to cook an onion, and that's a new word for VAL, cook. So it's a new task for VAL to learn, and it asks how to do that. I'm going to give it some steps. I start here with get an onion, and it doesn't know that either. So it recursively asks me how to get an onion, which I explain. And then VAL backs back up, and it says, well, the next step is put, and I don't know that either, so I'm going to ask for those steps. And it goes through this as I explain all of the steps, and you can see VAL on the right-hand side executing these actions as I'm explaining. And finally it's going to turn the pot on, and the onion is cooked in the pot. Now that's all I asked VAL to do, and now it has definitions of all of those words. So here's a general view of the flow of data through VAL, and that structured knowledge that you can see is a representation of the task that I just taught it. The dialogue at the top, which is what you saw me teach in the video, is interpreted by an LLM. We used a ChatGPT API, and that's responsible for mapping it to known actions or asking what does that action mean if it doesn't already know the action. So yeah, this conversation was hierarchical, which allows us to induce a task tree from it. where getting the onion is a substep of cooking it, and moving to the onion is a substep of getting it, and so on. Note that all of the leaf actions are just move to and press space, which are the primitive actions that we gave VAL in the overcooked environment that we're using. So one last thing to note is that the LLM did in fact decide that the onion should be generalized to arg1 here, but the pot should remain constant because the pot is the only way to cook something in this particular setting. And finally, you can see that that knowledge can be fed back through the LLM in the reverse direction to generate English again. So VAL can not only perform the task in the environment like we saw in the video, but it can explain tasks or subtasks if the user wants to audit the knowledge, or even if the user doesn't know how to do something and they're given a trained VAL model to explain it back to them. So, one last thing is that from that explanation of cooking an onion, and it generalized that onion to object, and now we can see that the sub-behavior can be invoked in a completely different setting where I say grab a tomato. I didn't use the word get, I said grab, which it was not trained on, and I didn't say onion, I said tomato, and still the LLM is able to map grab to get and fill in the argument slot with the tomato instead of the onion. So just to quickly recap before we move on, VAL uses recursive dialogues, and the recursiveness is clarifying unknown words and clarifying the substeps used to define those unknown words recursively. It uses these to form a recursive task knowledge tree, so knowledge of which tasks are subtasks of other tasks. And it uses GPT-based subroutines within a classical algorithm to understand the instructions from the user. And so we're going to go into some more detail about that. But just quickly first, I'll note that VAL's primitive actions, which are those for which it never seeks, and if VAL were applied to a web browser, for example, it might get access to the DOM elements of the web browser, or maybe simply mouse clicks and keystrokes. We chose to test VAL's task learning ability in this popular game environment called Overcooked AI. And that's based on an even more popular game called Overcooked, which I personally recommend as a supremely fun way to start hating your friends. Regardless, in this simplified environment, the objective is to cook different food items, like an onion or tomato soup, and you do this by placing ingredients in the pot, turning the pot on, plating the soup that's been cooked, and delivering the soup to the drop-off location. In that environment, VAL's primitive actions are moving to a location and pressing the spacebar, as we saw in the leaves of that tree before. So let's discuss recursive dialogues a bit more, and the knowledge representations that VAL learns from them, because those are really essential to the system. This is a transcript of me teaching VAL to cook an onion, where VAL is V and I'm U, the user. And this transcript is taken from the video that we saw earlier. This is what I typed to VAL. If my explanations are treated as left to right lists of nodes, and VAL's clarifying questions are treated as the edges, then we can see the form of the task tree that's learned here already just from rendering the conversation with those two steps. So you can see the subtasks branching off of supertasks under the clarifying questions, and the leaf nodes are all of the primitive actions moving to something and hitting space. Here's that same tree that we just saw after the LLM was used to form these formal predicate argument representations of those actions. So the words like cook and put and turn on are preserved, and the LLM uses them to form predicate names, which lends interpretability to the tree while keeping it as a formal logic structure. And because it's a formal logic structure, the tree is a completely reliable knowledge structure. So when you use it to perform this action, it will always give the same result. Furthermore, look at it. You can understand what the words are and what things are subtasks of other tasks. So if you believe that VAL learned a task incorrectly, you might not have to go through the whole process of training again. You might be able to just make a tweak to the tree. Now that we've explained the basic philosophy of VAL, let's talk about how we use the LLMs to bridge the language symbol gap. VAL is essentially a classical algorithm. We call it the VALgorithm. I call it that anyway. And within the VALgorithm, certain subroutines are invoked. Some of these subroutines are implemented classically, just looping over some data, but some of them, like finding the list of commands in a string that the user typed, or choosing a primitive or a previously learned action to map to one of those commands, those are implemented using carefully designed LLM prompts designed just to handle those tasks alone. As you can see in the VALgorithm pseudocode, the purple boxes are denoting LLM implemented calls, and you can see that the LLM is not the driver in the VAL architecture, it's more like the passenger. So the main structure of the algorithm is classical, and the subroutines of that algorithm are implemented with GPT. The GPT is not in charge of the algorithm. And so in that way, you're generally getting the same types of result each time. You don't have that sort of inherent variability that GPT can give. On the right are some examples of inputs and outputs that describe some of these GPT functions. I'm going to linger a bit on this slide at the end during questions so that you can digest it a bit more. But for now, I'm just going to say that each subroutine is a naturally segmented micro task. Segmenting the text into actions, mapping each of those actions to something you already know. And so we're not trusting the LLM with any big end-to-end task, like, hey, here's the utterance, give me a list of primitive actions that does the task they want. That sort of end-to-end thing doesn't give us a reliable structure in the middle. And so segmenting into these micro tasks is essential to getting an interpretable and reliable knowledge structure out of VAL instead of just a sequence of actions. Let's talk about evaluation. We performed a user study to evaluate VAL's understanding of what people say and VAL's efficacy at performing the final task that they tried to teach it. Like the classical NLP pipeline I called error-prone earlier, VAL's pipeline structure also admits errors, albeit a smaller number because the LLM steps have abstracted away entire NLP pipelines, so that class of error has been removed. Nonetheless, these LLM subroutines can introduce their own errors that compound into future steps because it is a pipeline. And so we needed a mechanism to handle that, especially in the initial studies. So we had our study participants confirm or correct every single GPT subroutine call, mapping actions, generalizing arguments into variables, grounding specific objects in the world from nouns that the user provided in the utterance. All of these were given to the user to say, like, hey, was this correct? And if not, what was the actual answer? The users understandably found this kind of annoying, but it was necessary because not only did we have to judge the correctness percentage of each of these calls using their ratings, but we had to allow the interaction to proceed if it was wrong. And so we had to seek a correct answer from the user if it was wrong. Otherwise, the rest of the steps would be compromised by the incorrect determination earlier in the pipeline, as well as measuring those individual LLM components' accuracies using the confirmatory dialogues. Each participant also took a survey after their session, and we asked them several questions that we collected and unified from other task learning system user studies to try to cover the bases. Participants answered using 7-point Likert scales, or is it Likert? I honestly don't know how you pronounce that word. Someone will tell me in the question and answer session. But they answered with 7-point Likert scales that indicated the strength of their agreement with each of these claims. And I'm going to focus for now on our lowest scored question, which is that VAL learned the task without me needing to correct it often. So I think that highlights that despite the relatively high user approval rates for each individual LLM subroutine that we're about to see, users still felt like VAL was asking for too many corrections. Even if every component had 90% accuracy, just to do a little math here, there are still 5 correctable pipeline steps, and the chance of having no errors originating in any of those components, even assuming they're independent, plummets to 59% of the time, even with 90% accuracy on each of them individually. So correcting each component for maximum accuracy is going to be essential, especially the ones earlier in the pipeline, so that things don't compound. The confirmatory dialogues in the study, they allowed us to measure the efficacy of each of the LLM subroutines, and they were generally decent, cascading errors notwithstanding. But I want to point out that the map GPT subroutine, which maps action phrases like go to the pot or grab the tomato strings, it maps those to known actions or says that it can't. We actually gave this a separate component, which was a validity checker for it. And the way that that worked was it asked whether the input phrase and the verbalization of the mapped action are paraphrases of each other. It asked GPT this question. And GPT would say, yes, those are paraphrases, they mean the same thing, or no, they're not. And we compared that to the user decisions in the confirmatory dialogues, and we saw that it had 21% false negative, but only 1% false positive. So that means that if we were to use this validity checker based on paraphrasing to accept all of its decisions, we would save 80% of user confirmed prompts with only 1% error. And so I think that sort of thing, finding validity checkers for any of the components that have a low false positive rate that you can trust is essential to removing the number of confirmatory steps while preserving some amount of accuracy. That's all for now. I guess actually there is no question and answer session because I'm recording this for online, but you can feel free to email me, lanelawley@gmail.com. I'll linger on this slide for a little bit so that you can digest it. But I'm going to get up.